I'm happy to invite Anna, or to introduce Anna. And I lost my schedule now, of course, who will be talking, Anna Cepek, from the Institute of Basic Science in South Korea. And she will be talking about configuration spaces of ℝn and Joyal's theta n category. Thanks for joining us, Anna.
Yes, thank you for the invitation, and thank you to the organizers for putting this on. Okay, so yes, today at the heart of what I'm talking about is configuration spaces of points in Euclidean space. And now I've written a definition of the configuration space of our points in Euclidean space. And just to connect it to the big theme of the conference, which is operads, as you vary cardinality, there is the structure of an operad in these configuration spaces. And that's in fact the ℝn operad. But for my talk, I won't be talking about this operatic structure. However, through the configuration space, because it's in the ℝn operad, the content of my talk has some pretty close ties to ℝn operads and algebras over ℝn operads. So Ayala and Hepworth a while ago showed that there was a relationship between configuration spaces in Euclidean space and Joyal's theta n category. And they did this for the ordered configuration spaces. And to some degree, what I'll talk about today is the unordered version of that. So the unordered configuration space is obtained by taking the quotient of the natural action by the ℝth symmetric group on the configuration space. This action is given by just permuting the indices, and you arrive at the quotient space, which is the unordered configurations in Euclidean space. And I will be focusing on the homotopy type of these unordered configuration spaces and giving some intuition for why they can be understood combinatorially in terms of the theta n category. So here's an overview. Perfect. Yeah, first I'll encode these, the homotopy types of these configuration spaces of Euclidean space with a certain infinity category. And then we'll look at some intuition for the relationship with this infinity category to the theta n category. Oh, that's not, okay, great. Yeah. Okay, so to begin with, for the entire talk, M will be a connected, smooth manifold. Now these configuration spaces, unordered, as you vary cardinality, they organize as a topological space together. And this topological space is called the ℝn space. So the ℝn space of M is the set denoted ℝn of M of just all finite subsets of M. Except the empty subset. And we will give this set the colimit topology, so meaning the finest topology for which the maps from the M fold, from the M fold, or the R fold product of M with itself to ℝn of M, given by just taking this R tuple of points in M and sending it just to the collection of those points. Yeah, so the finest topology for which these maps are continuous for all R bigger than 1. Okay, so I want us to just take a moment to think about the ℝn space. So what is life in the ℝn space like? Well, a point in there is a finite subset of M. And if I move a little bit under this topology, that means I'm watching my points move around continuously in M. And also, because I have all finite subsets of M, I can, movement in the space looks like points subdividing into any finite number of points, or as they get close, as 2 points get closer to one another, colliding. Yeah. And maybe I'll also note that the ℝn space, it's wildly infinite dimensional, but it actually is kind of an interesting space in the fact that it's weakly contractible, which is just an aside. Okay, so yeah, again, a path in the ℝn space looks like anti-collision of points into finite subsets of points and collision of points. That's life in the ℝn space, all happening on the manifold M. Okay, another thing we can notice about the ℝn space is that I can remember just the cardinality of each point in the ℝn space, and that gives me a map to the natural numbers. So there's a map given by cardinality to the natural numbers. We take this finite subset in M and just remember its cardinality. And the fiber over each natural number is just the configuration space of R unordered points in M. Okay. Now this map indicates that there's some extra structure with the ℝn space, and that structure, namely, is stratification. So the ℝn space is an example of what's called a topologically stratified space. So in general, a topological stratified space is a couple of bits of data. So first, it's a Hausdorff paracompact topological space. A poset P, but we are going to regard the poset as a topological space as well. So the poset P with the upward closed topology. And what does this mean? This means that open subsets just go up. So U subset of P is open if A being in U, and there being some element in P that's bigger than A, then that element is also in U. Okay. And the last bit of data is then a continuous map. From the topological space to the poset, such that each fiber is connected. Okay, so before we get back to the main example of stratified space, which is the ℝn space, let me just give a couple examples that will behoove us to know for later. Okay, so we can stratify in a trivial way the 0 simplex, which is just a point. We can stratify it with the poset consisting of just one element. So that's not very exciting. But more generally, we can stratify the 1 simplex. And I'll kind of draw the 1 simplex in a bit of a funny way to indicate the stratification. So this topological space is stratified by the poset 0 less than 1, which is, none other than, in notation for the simplex category, bracket 1. And what is the map? Well, I've indicated this point is the 0 stratum, and the segment, the half open segment from here up to the top is 1. So I'll just indicate that with 0. This point gets sent to 0, and all of these points get sent to 1. Okay, and then delta 2 similarly can be stratified, and this stratification of the topological simplices is called the standard stratification. It's very helpful for understanding the infinity category that I'll define in a moment. So let's see. Yeah, so for the 2 simplex, I'll draw it kind of like this. So I'll kind of break up its stratum. It's stratified by the poset linearly ordered set. So that point gets sent to 0. Again, this whole line, half open line, gets sent to 1. And then everything else is the 2 stratum, open there and then corners. Okay. And so on and so forth. You can maybe imagine the stratification of a general topological simplex. Okay, so back to the main example, the thing we really care about, the ℝn space is in fact an example of a stratified space. Its stratifying poset is the natural numbers. The map is given by cardinality, and the stratum are precisely the configuration spaces of the manifold. Okay, so because the ℝn space admits this structure of a stratification, there's a construction that we can use, which takes in a stratified space and spits out an infinity category, and this is called the exit path infinity category. So for a stratified space, X over P, the exit path infinity category of X which is denoted exit of X is the simplicial set in which an object is a point in X and a morphism is a path in X. Oh my gosh. Oh, I just turned an iPad off. Ah, sorry. Whoops.
I think that just keeps everyone's awake. Like we're
keeping you on your toes. I think I have to. Oh, I think I have to do it all. Okay. So, it's like you're on the edge of your seat, wondering what is a morphism in the exit path infinity category. Oh, what could it be? Okay. And maybe this is a good time to pause. I feel like the online thing is a great alternative to in-person, of course, but I think it comes at the cost of maybe I don't know if you're all following me or whatever. So if you have questions, feel free to speak up now while I'm slowed down.
Actually, since I do have a question, I was going to hold till the end, but could you say a little about how the strata were the configuration spaces? I just sort of missed it in your example of the round space.
Yes. That's a really important aspect. This is kind of central. So that's a great question. So the Ron space as a stratified space, I guess I didn't say this terminology. For a stratified space, the P stratum, so I guess I should say for a general stratified space, the P stratum is just the fiber over P. And so for the Ron space, if we think about, well, what lives over the natural number R, well, that's all of the unordered configurations of R points in M. So that's the, each configuration space then is a stratum of, or a strata of the Ron space.
Great, thank you.
Yeah. Okay. So a morphism is a path in X, but it's not any path. We're only taking certain paths, which one could call them exiting paths. So namely, we want these paths to remember the stratification of X. So a morphism is a path in X that is allowed to move from a stratum to a less deep stratum, but not vice versa. So let's think about a morphism for a second. in one of our examples. So let's see, take maybe a blue. So let's look at the two simplex and think about what, so paths in the two simplex are just paths in the two simplex. But if we want to talk about particularly these paths that yield morphisms in the exit path infinity category, called exiting paths, and I think I'll write that, exit path. Oops. Well, we want to go from a stratum to a less steep stratum. So for example, we could start at 0 in our path and then swim into the 2 stratum, for example, or we could start at 0 and go up to the 1 stratum, or we could start somewhere in the 1 stratum and then go into the 2 stratum. These are all exiting paths. But if I were to try and go back, take the reverse of any of these paths, those are not exit paths. You can think of it as these paths need to respect the stratification. They need to go up with the stratification. Okay. Right. I think I had something else I wanted to say about that. Well, anyway. In general, let me tell you what this simplicial set is. I told you on bracket 0, bracket 1. In general, oh, whoops. Oh. In general, exit of X on bracket K is defined to be the set of all maps from the K simplex into X such that F is a stratified map. So meaning it's a map of stratified spaces. And maybe I'll just write out what this means. A map of stratified spaces really means a map between the topological spaces together with a map between their posets, such that this diagram commutes. So maybe if you've seen this before, or if you're feeling good about what I'm talking about, you can see these examples of the standard stratification of the topological simplices. Why that's a helpful thing to think about when thinking about the morphisms and two morphisms and so on and so forth in the exit path infinity category. Really, we're just looking at maps from the simplices into our stratified space to name these higher morphisms. Okay. Oh, good. So let's get back to the main example, which is the exit path infinity category of the ℝn space I guess I'll just say I have a manifold for now. So what's an object? Well, that's just a point in the Ron space, which is a finite subset of points in M. And a morphism is a path in the Ron space that respects the stratification of the Ron space. So that means, remember, the stratification of the Ron space is given by the natural numbers. Here's the stratification. So we want to take paths in the Ron space that go up with the natural numbers. So namely, we're watching points split into finite subsets, but we cannot go down with the natural numbers. So that means we can't watch points collide, because that would take me from some higher cardinality to some lower cardinality. So heuristically, we can describe the morphisms of the exit path infinity category of the Ron space M as paths in Ron of M that witness anti-collision of points, but not collision. Okay. And I remember what I wanted to say earlier. Technically, for morphisms in the exit path infinity category, and maybe you could deduce this from this general description, but they can't just move willy-nilly from one stratum to the next. They have to either exit immediately or not at all. So I should say they're allowed to move immediately. And you can just think about mapping the topological one simplex, that's going to give me a morphism, into a stratified space. And this guy can land on a point, and then, or the zero stratum can land on a point, and then the whole one stratum needs to be in some other stratum, or else it can just stay in the same stratum. So back to the Ron space, these paths witness anti-collision of points immediately at the start of the path, or not at all, and points can never collide. Okay. And a way I like to draw these morphisms is by drawing their graphs, because really these paths in the Ron space are just collections of paths in M that behave a certain way. So we could draw, for the case M is R3 or R2, whoops, R2. We could draw an object, some finite collection of points in R2, and think about, well, what's a path, or what's a morphism whose source is that point and whose target maybe is this point, and we can draw the graph. And kind of like this. Or maybe this guy splits into 3 points. This guy doesn't, and that guy doesn't. Ooh. Okay. So this is how I like to draw or think of morphisms, as pictures like this. Okay. And of course, you know, you can do some braiding, things like this, and that's where the configuration spaces of Euclidean space get interesting as far as their homotopy types go. Okay, one last thing to note before we try to see some combinatorial business happening is that the underlying infinity groupoid of the exit path infinity category of the Ron space is just the disjoint union of the configuration spaces. So let me write that and then say a word. The underlying sub or maximal sub infinity groupoid of exit Ron of M is the disjoint union of the unordered configuration spaces. And why is this? Well, to think about the underlying maximal subgroup infinity groupoid, we want to think about, well, what are the paths in the exit path infinity category of the Ron space that are invertible? And those are precise, or what are the morphisms, rather, sorry, that are invertible. So yeah, which paths can we reverse? And we can reverse all of those paths that stay in the same stratum. So all the paths that don't ever split, witness splitting points. Because as soon as you split a point to go back on that path in the Ron space, you have to collide the point. And that's not an exit path, that's not a morphism. So in this sense, the exit path infinity category of the Ron space of a manifold encodes the homotopy types of the configuration spaces. Okay, so moving on to part 2. Now that we understand a little bit about this infinity category, let's think about in the case that our manifold is Euclidean spaced, and I'll draw some pictures to show some intuition for the combinatorial nature showing up in it. So, okay, so here's a main theorem. There is a localization of infinity categories from the theta n category and some subcategory of it to the exit path infinity category of the Ron space of Rn. And in the case n equals 1, there is an equivalence from some subcategory of the simplex category to exit Ron of R. Okay, so with the theta n category, I don't expect people to be super familiar with that necessarily, but I'll say maybe a few words about it to give someone who knows nothing about it an idea of what's going on with the theta n category, and if someone knows a little bit about it, maybe you can see the picture a little bit better. So the theta n category is a sheerly combinatorial object. To give its definition justice takes some time, but in the case of n equals 1, the theta n category, theta 1, is just the simplex category. And just to remind us what's the simplex category, objects are finite, linearly ordered sets, and the morphisms are non-decreasing maps between these linearly ordered sets. And so to think about the intuition for why this theorem is true, we'll start with the n equals 1 case, thinking about the simplex category. So for n equals 1, let's think about an object in this infinity category and see if we can cook up or extract some combinatorial way of seeing it. So an object of x at ℝn of R is just a finite subset of R. And maybe I'll just tell you what the assignment is. This map assigns the 2 simplex to that object in the x at ℝn of R infinity category. And bracket 2, oops. Bracket 2 is, I don't know why it likes to do the eraser. Okay, bracket 2 is the linearly ordered set 0 less than 1 less than 2. And I like to think of that bracket 2 just living over my linearly ordered set. And you see we kind of reverse roles here. The points in the linearly ordered set become the gaps, and the gaps could become the points. And that's what I mean by that. Gaps become the points. Okay. And now let's think about a morphism in x at ℝn of R. So a morphism can witness anti-collision of points. So let's say this guy splits, and this guy doesn't. There is a morphism, and living over this guy is the 3 simplex by taking gaps. And you can see that there's a natural assignment, a non-decreasing map from bracket 2 to bracket 3, kind of encoded with this morphism. So by looking at the gaps, so 0 goes to 0, this gap tells me 1 goes to 2, and this gap tells me 2 goes to 3. So there's the assignment, there's the equivalence. Maybe I'll just write this down. 0 goes to 0, 1 goes to 2, 2 goes to 3. So first, I'd like to point out that it always feels a little uncomfortable to name a map from an ordinary category to an infinity category, just because with infinity categories you have spaces, so that makes things feel a little hairy because I'm mapping some discrete thing to some non-discrete thing. But really the space the space of all 2-point subsets is a contractible in R is a contractible space. And so this assignment on the level of objects is well defined. And similarly, assigning this morphism to that morphism too is well defined, because if we fix source and target and we think about this space of all of the morphisms, all of these exiting paths where this guy splits into two and that one doesn't, that forms a contractible space as well, yielding a well-defined assignment on the level of morphisms. Okay, and the last thing for this simple case is just thinking about, well, what is the subcategory of the simplex category that gives us this equivalence? And you'll note that anytime I draw an exit path in ℝn of R like this, the map is going to carry 0 to 0. So 0 will get carried to 0. And whoever is on top will get carried to whoever is on top in the bottom. So this sort of morphism in the simplex category is called active. So this is an active morphism. And also, we can notice that we'll always end up with an injective map as well, looking at just kind of the behavior of these exit paths in R. So the subcategory is active and injective morphisms. Oh, and we do not ever think about bracket 0. We don't consider the empty subset for this infinity category. Okay. So for the more general situation, for general n, I think I'll focus on the case of n equals 2. And I think that that situation yields a lot of the intuition that happens for general n. So we'll think about when n is 2. And I will give you a definition / a partial definition of theta 2. So first, theta 1 is defined to be the simplex category. Then here's a full definition, and if you're familiar with Riesz product of categories, then this definition will be no problem, and you probably already know what theta 2 is then at that point. But theta 2 is the Riesz product of the simplex category with itself. But if you don't know what the Riesz product is, I'm not going to take the time to explain what it is, but instead ignore that, and I'll say, or theta 2, I'll describe the objects of theta 2, and unfortunately not the morphisms. So theta 2 has objects which are called planar, rooted, level trees of height 2. So let me draw one of these. So there's our root. The root is a sheerly formal thing. That's the root. Planar means we put them in the plane. Level means there's different levels. So when we have a height 2 tree, that means we have 1, 2 levels. So here's the first level. One, and then from there we can go up to the second level. 2. And the branches don't have to go all the way up to the top. And if that's the case, then the tree is called unhealthy. Otherwise, if all of the branches go up to the very top, it's called a healthy tree. So 2 level. Okay. So yeah, this is an example of an object in theta 2. And really, the objects in theta 2 described in this way makes the relationship to configurations of points in Euclidean space really quick, at least intuitively it does. So, all right. Healthy trees. And by tree, I mean this whole, whole spiel, planar, level, rooted, blah, 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 trees. Healthy trees encode finite subsets of points in, I guess for our situation, it's R2. And maybe this being said, you could imagine what theta n. Theta n has height n rather than height 2 trees. Okay, so healthy trees encode finite subsets of points in R2 together with their coordinate coincidences. Okay, so what do I mean by this? Well, let's draw some pictures. And maybe go back to the main theorem. So we want to think about what's the relationship between theta 2, well, some subcategory of it, and exit ron of R2. Well, let's look at this tree. So I'm going to forego the little dots because so I'll be lazy now. Okay, so this tree, this first level is really telling me about the projection onto the first coordinate, and the top level of the tree is telling me about how many points I have in R2. So this tree corresponds to any subset in R2 that looks like this, where they have their first coordinate in common. So this is our axes. Okay, and a tree like this tells me that I have 2 points in my plane. And their first coordinate, because these are distinct here, their first coordinate is not the same. So any finite subset of 2 points that do not agree on their first coordinate, that is exactly what this tree encodes. Okay. Yeah, so this essentially is, I've just named for us the assignment of this map on the level of objects. And I'll just note, again, we're making an assignment from a discrete, from an ordinary category, so discrete sets to things that really have spaces. And so this tree being assigned to this 2-point subset, well, if we think about all the different 2-point subsets of R2 that live on top of each other, that is a contractible space. And similarly for this guy. Okay. And now let's think about morphisms. So I've told you nothing about the morphisms in θ2. And unfortunately, with the description of objects in θ2 as planar level-rooted trees, it comes at the cost of the morphisms are pretty hard to describe. Okay. Should I? I think there's a question. Should I?
Yeah. Sorry, I was.
Yeah.
Is there a morphism between those two objects, or are they? I mean, you don't necessarily have to describe it, but does one exist? Because there is one
in θ2.
Yeah.
Yes. Yeah, there's a morphism. Okay. Just one, or actually, there's two morphisms going that way.
Okay. And
none going the other way.
Okay. And does it correspond to the braiding, or?
No. So, and this is kind of the fun part. The braiding tells us an awful lot about what the localization needs to be. Like, what do we need? So, to remind us, what's a localization? Well, informally, to say that there's a localization, it means that there's some subcategory living inside of θ2, such that if I force all of the morphisms in that subcategory to be isomorphisms, so I just give them all inverses, then I end up with exactly ℝn of R2. So localization means force certain morphisms to be isomorphisms. So we want to think about, well, what is that localizing subcategory? Maybe why does this map fail to be an equivalence? Yeah, and why do we need to localize? So yeah, let's think about an interesting morphism over on the left side from this 2-point subset to that 2-point subset. Well, a fun one, of course, is braiding. So there is a morphism, and I'd like to point out that this morphism is an isomorphism in ℝn of R2 because we're staying in the same stratum. I can go back. I'm not splitting points, therefore I'm invertible. Whereas on the other side, I'm not going to tell you what morphisms in θ2 are explicitly, but I'm going to give you a fact about a key fact about morphisms in θ2, which is the only isomorphisms in θ2 are automorphisms. And so over here, my source and my target trees are not the same tree. They're different trees. And therefore, any morphisms between them are not isomorphisms. So in particular, that means I do not have it. If there isn't a morphism going down, which there is, there's no morphism going back, that is its inverse. So that is kind of a problem looking at this morphism over here. So there it is, not exist. And this cannot be an isomorphism. Okay. So this, let's see, this kind of gives some intuition for what the localizing subcategory should be. Namely, we want something like this to be invertible. So if we force whatever that morphism is going down to be invertible, then that's at least like, that's a desired property. So, or a desired thing. So, yeah, let's see. So maybe I'll kind of describe, oh, and you know what, I should say this, sorry, I should definitely say this. So as it turns out, the map going this way does not land on this morphism. In fact, this morphism can only be cooked up after we localize on the appropriate subcategory of theta 2. And let's look at why. So remember, oh yes.
Oh, just to let you know, we've got about 5 minutes left because we started a bit late. Yeah.
Yes, okay, perfect, thank you. So remember that the assignment between tree and finite subset in R2 really came down to remembering the projection onto the first coordinate. So if we think about, well, what's happening if we project this whole path down to the first coordinate? And so let's think about what that is. So if we project this path down, we've got something that looks a little interesting. It's going to look something like this. And this is kind of funny because what is happening if we project down to the first coordinate and look at the induced path down there, we've got collision happening because of the braiding. And in fact, this is kind of this is kind of the whole point. So if we slice this morphism up into little morphisms, we can see that little morphism corresponds to some morphism like this. And this morphism wants to correspond to some morphism. Wants to correspond to some morphism like this. Oops. But in theta n, there does not exist such a thing. And so on and so forth. So maybe I'll say, so from all of this, we can say that the localizing subcategory theta 2 is all consists of all of those morphisms that induce bijections between the sets of leaves. So something else about theta 2 is, which maybe you could believe, there's a map for each morphism in theta 2, there's a map induced then between the leaves. And actually the map goes the other way than the original morphism, but those are precisely the morphisms that we will invert in theta 2. And upon doing that, then we can cook up strings of morphisms like this and get all of these braidings that give us the interesting homotopy types going on with the configuration spaces. And okay, 1 minute, just really fast, because I think this is slightly, hopefully it's not too unsettling, but like I said, this morphism, this braided guy, is not in the image of this map. It is in the image of the map once we localize theta 2. So maybe it will be a little bit satisfying to know, well, what is in the image? What does this morphism, for example, get sent to? Well, it gets sent to something that looks, it's not going to braid, of course, it's going to stay in the same 2 stratum, but it just goes from being coordinate coincident on the first coordinate to not. So here's the image of one morphism like this. Okay, yeah, so that's all the time I have. This talk is based off of a paper that I have up on the archive. So if you're interested, feel free to look at that. But yes, thank you for your attention.
Thank you very much, Anna.